So if you've been following any of my posts and such, for the past couple weeks, I've been working on a rather interesting project to get a Seeburg Wall-O-Matic Jukebox controller to work with my own custom circuitry to talk to a Sonos system. So right here is the Wallbox I've been working with. This is a Wall-O-Matic 100, which is a much simpler mechanism than the 200 that I started with, which I had some early problems with. And I've got it all assembled now, finally, and on this nice little overbuilt base that I'm working on. And let's take a look at the circuitry I've been putting together. So early in development, I built a breadboard version of all the schematics that I've been working on for this project, just to prove that all the components worked. And this actually is fully functional. It has all the major components for handling the pulses, relays for triggering the coin switches, debouncing on the output of the pulses, regulator, a Adafruit dev board version of an ESP8266 can be plugged in right here, and it actually does work. However, this is obviously not something we would actually want to install in a product. So, I did actually design a PCB, which I got through Oshpark. This is the package for the Revision A boards that I got. And this is what it actually looks like when it came out. And I've actually assembled one of these already. Right over here. This is the Revision A of the Wallbox interface, but as you might be able to see here, and more importantly, back here, Revision A wasn't exactly perfect. There were some problems identified, which I did correct in the schematic, and did a new, fresh layout of this board to make it smaller as well. As you can see, it's also pretty big. However, this version does actually work, and it's been quite useful for testing. So the PCB for Revision B just arrived today, and so I'd like to do a little unboxing of it. So here's the wonderful envelope that it came in. Let's open it up. And inside, there's your standard Oshpark envelope. Perfect purple PCBs manufactured in the US. So now let's open this up and let's see how Revision B actually looks. Here we go. This is the Revision B of the Wall-O-Matic interface. If you look closely, it's actually smaller than Revision A. By quite a lot, actually. My goodness, look how much I took out of the size of this thing. It's basically everything's more condensed, closer together. There have been a few minor changes. I fixed the messed up trace from this one. I took out this diode that I later discovered was actually a bad idea. I fixed some of the silk screening over here, fixed the footprint of this regulator, and yeah, I just did a general sort of condensation. So the next step is actually going to be to collect all the components to assemble this and to actually put it together. So now that the board's all unpacked already, I've filed off the little notches that Oshpark leaves on the side. It's time to start getting ready to put this thing together. So I've got my soldering iron and solder spool all ready to go. And most importantly, I've dug through my parts bin and I've laid out all the components I'm going to need to put this thing together. One thing that was really helpful in doing this is I actually have an extremely detailed bill of materials from KiCad as part of the design process. I made sure that I actually had complete BOM data for every single component on this board. So you can actually export this, import it into DigiKey, and populate a cart with everything you need to put this together pretty much automatically. And everything here has been ordered from DigiKey with the exception of the resistors. I had a resistor collection that I accumulated from Jameco many years ago, all the standard Jelly Bean resistors, and so for those I just use those. For capacitors, I actually did part out from DigiKey just to make sure I knew the actual dimensions of all of them for the PCB layout, and to make sure that I was getting them from quality brands. So if we look at the selection of components, this is pretty much everything. You've got your resistors, capacitors. Those blue ones are actually very hard to read what's on them. When I built Rev A, I actually put them on a piece of paper where I had the value written. These are the relays for the coin switches. That's our Schmidt trigger, some buttons. The opto isolators was interesting. I originally ordered a version that came in a DIP 4M package, which were a little wide, and I just had to bend the pins into shape, and they fit okay. But then I found out they make them in a normal DIP 4 package, and so I just ordered those, so these should fit a little bit better. Over here, we've got the DC-DC converter for the ESP8266, some pin headers, the diode bridges, and the ESP8266 module itself, and ESP12S. This one is actually the Adafruit distributed one sold through DigiKey. When I built the Rev A board, I used the ESP12S sold through Electro Dragon. On the outside, they're identical, except this one costs about $2.40 plus enough shipping to cancel out any savings, whereas this one is closer to $7. However, once I assembled this board, I suddenly discovered that this unit only has a megabyte of flash, whereas I had been led to believe the ESP12S actually has 4 megabytes. When I went back to Electro Dragon's website to figure out what the heck had happened, I discovered that all units sold from some date after I placed my order now have 4 megabytes. So apparently they've fixed the issue. However, shipping was enough that I just decided to play it safe, order the Adafruit DigiKey model of the same module, which I know will have 4 megabytes of flash. Now, thankfully, the firmware I'm developing actually fits okay within 1 megabyte, but, you know, might as well just future-proof the thing. So this is everything that I'm going to need to get started, and I will get to the assembly process shortly. Okay, let's get started with the assembly. Okay, now that the board's fully assembled, except for the ESP12S module itself, it's time to start testing it and make sure that, nothing explodes and that everything is working correctly. Since soldering in the ESP12S is mostly reversible, it's not very easy to remove, I'd like to make sure everything else is okay first. So I've connected a transformer that should be outputting the necessary voltages over here. And we'll start by doing some basic multimeter tests. So let's switch my multimeter on. We'll begin with AC. And let's see what happens. Okay, power is live. So let's see. Our transformer is reading 28.1 volts off the main rail, 14 volts off the center tap. On the other side, we have the power that's supposed to go to the Wallbox. That's also reading the appropriate amount. That's all good. Okay, we have a few more base voltages that we can test. The regulator for the microcontroller right here. That is going to be DC. In fact, the rest of these are going to be DC. So that one should be reading 3.3 volts. Let's see. Yep, close enough. Okay, the other thing is the relay power supply. The relay power supply should be reading 5 volts between the latter two pins of that regulator, or to keep things simple, across the leads of this diode. Yep, 5 volts. Okay. Next thing we should do is test and see whether we're getting everything correct on the pins for the ESP12S. So I've got the schematic and a data sheet showing the pin out of the module in front of me. So, first thing is the reset pin should currently be pulled high unless I push the button. So, let's measure between ground and reset. That's pulled high. If I push the button, it drops low. Excellent. Okay. I should also be seeing pull-ups on pins 12 and 11. So this would be 11, 12, looks good. Program pin here, this one just shorts to ground and there's a jumper on there. Otherwise, it should be reading high, so I should be able to read the full voltage across this. That looks good. The configuration button, that one is just going to short directly to ground. There's really not much we can test unless we want to do a continuity check, because that relies on an internal pull-up on the ESP12S. So the next thing we should try is the relay triggering. So for relay triggering, basically, what's going to happen is if we look at the schematic here, when the relays are triggered, what's going to happen is the 25 volt line will connect through to these different lines right here. So what we'll do to test that is set ourselves back into AC mode. We'll stick a pin, multimeter lead, loosen these up a bit. In there. And we'll start with the 5-cent one. If that even works. Yeah. Okay. that worked. Okay, let's test the 10-cent relay. 10-cent relay is going to be on pin 6. These are all over the place. Pin 6 is the third from the top on the other side. So let's stick a wire in there to power. Excellent, that worked. And the last one is the 25-cent relay. And these cents are really just the different coin switches inside the wall box are supposed to trigger. So this is the one for when you drop in a quarter. So 25-cent relay connects to pin 5, which should be the fourth from the top over here. Excellent, that worked. The next thing we want to test before we actually solder in the ESP12S is the actual wall box signals. And those are a little hard to test with a rig like that to see a realistic scenario. We really need to test those is a wall box and an oscilloscope. Okay, now this is where the fun begins. I've got everything set up here. I have my oscilloscope probe, I have my circuit board, and I have it connected to a wall box. So let's fire this thing up. Wallbox is live. Now we will set the oscilloscope to, which is set up here, to trigger on a single pulse with the right properties. And here goes. Before we begin, let's put in a coin. That way I don't have to go ahead and trigger a relay while I'm holding the camera. Go over here. Let's get on the probe, get the probe on the pin, key in something on the wall box. Let's look at our scope. I think it worked. This is exactly what we were hoping to see. Nice signal pulses coming off the wall box. I think we are ready to start soldering the ESP12S. Okay, let's see how my first attempt at using solder paste goes. Next thing to do is clean it off and see if it works. Okay, after plenty of cursing and frustration with finding shorts all down one side of this thing, and attempting anything I could with, solder wick and solder suckers not really designed for the task, I eventually used my not actually an SMD rework hot air gun to attempt to try to reflow the solder, and eventually, after a little bit too long, the module just basically popped off. And once it popped off, I stopped detecting the shorts. So I'm going to attempt to resolder it and see what happens. But at least I know, in an absolute worst case scenario, I actually can remove this thing. So this time around, let's play it safe and do it the old-fashioned way. Okay, we'll get our meter out. We'll not picking up ground on any of those remaining pins. That is a very good sign. Okay, let's throw some power at this, see what happens. Nothing. I sure hope I didn't break something in the process. Well, I did a little more fiddling with the soldering iron and the flux pen, and I think I got lucky. Now, when I press the reset button, I get a little blink, which is a good sign rather than nothing or solid blue, and I see something on my scope on the serial pin. So the great thing about having a scope with serial decode is I just configured it for the wacky custom baud rate that this thing boots up at. And we're going to do a single trigger, hit the reset button, and voila! CRLF space ETS space, it looks like these are the boot messages. I think I'm finally in business. So, this board appears to now mostly be working, and it's now time to actually try connecting a computer to it. Okay, so the last step is to try to hook this board up to my laptop and see if I can talk to it and possibly even download firmware. So the first step is we get this USB serial module, and we need to plug it into the board. So it goes there, goes there, and the last one goes there. Okay, now time to go over to the laptop and plug into the other end. Okay, now that we're all hooked up, I have a serial terminal program up and running and configured to the unusual 76800 baud rate that this thing spews its initial startup messages at. So the next thing to do is to power it on. There we go. Those are the initial startup messages. Okay, so the next thing we're going to try is trying to flash updated firmware on this device. So we put a jumper on the program pins on the board itself, reset it, and then run this complicated command that I put together from the documentation. So this is going to go ahead and write the correct recent firmware to the device, which is not really our program long term, but this is going to initialize the flash, blank out certain regions of memory, and give us that basic AT command set that should let us interrogate the thing. So it's just chugging along. It's done. Now we'll remove the jumper, reset again to be safe, and open up a serial terminal, now set to a much saner baud rate, and type in a command, and it looks like it's now working. Okay, now to load our own code, we have to put the device back into its program mode, which I'll do right now, and run a simple command. This should be flashing our own firmware onto this device, and when it reboots, we should see startup messages. Almost done. There we go. Okay. Let's pop open our serial terminal again. Reset. It looks like we are in business. So the final step of setting this up, assuming I've written the firmware correctly, is to actually start it in configuration mode. To do that, I hold down the new button on the RevB board called Config, press reset, and wait for it to start up. And now, once it does, it should go into a special access point mode where it shows my list of Wi-Fi access points as its own access point. So it'll do that. and maybe it will hijack my DNS and take me to the right page. But if it doesn't, there's a special URL that I can visit, which will bring up the Wi-Fi configuration page. Now, on this page, all I have to do is select my Wi-Fi network, type in the password, no SSL on this thing at the moment. Maybe I'll add that in the future. It's trying to connect. And it's connected. There's the IP. Excellent. Okay, so I've reassociated to my normal access point. We'll go to that address directly, and here is the Wallbox web interface. So to set this up, we basically have to pick our Sonos device. It's already discovered all the zones that I have in my house. We're currently in the lab in the garage, so I'm just going to select the garage zone. Then we go to configure Wallbox. We pick which kind of Wallbox we have. I'm going to be testing with a Seeburg Wall-O-Matic Model 100. Then we have to set our base folder path in the path that we have selected, which is this. I have a separate dedicated directory for Wallbox songs on my file server that Sonos is talking to. We'll populate the empty songs. Since my first couple tracks are actually M4A files, I'm just going to go and manually fix those. Okay, now I'm going to save my song selections, and this thing should be all configured. So the next thing to do is actually hook it up to a Wallbox and see what happens. Okay, it's finally time to wrap this whole video up and do our final end-to-end test of the board we just built. So we have our Wallbox, our fully assembled Wall-O-Matic interface board, and a laptop for talking to its web interface, so we can insert coins. So I'm going to flip it on. We'll wait for this thing to start up. Once the blue light turns solid, it should associate with Wi-Fi, which it has. So now we're going to make sure the web page loads. Time to insert a nickel. When I click this, you should hear a clunk and that light should come on, which it did. Okay, we're now done with the laptop. Now for the fun part. Going to pick a song and see what happens. And there we go. It works.